Hi children, welcome. Welcome to another class. In this video, we are going to discuss chapter solutions. Second year topic, chapter solutions. Unit 2, solutions. All of you know what are solutions. Solutions are homogeneous mixture of two or more components whose composition can be varied within certain limits. Solutions are so defined. They are homogeneous mixtures containing two or more components whose composition can be varied within certain limits. If you go through the introductory paragraph of NCERT itself, you can find one or two objective questions where you find the points like certain alloys. There is a talk on certain alloys like brass, German silver, a mixture of copper, zinc, nickel. There was an old question, what is the percentage of silver in German silver? A very tricky type question. There is no silver in German silver, it's only in the name, German silver, bronze. There is a talk on, you see, sodium fluoride used in rat poison. So there are certain one or two objective area you can find in the introduction topic itself, right? Then there is a classification of solutions. Classification of solutions. All of you know a solution contains solute and solvent. There is one component called solute which is getting dissolved in a amount of solvent. That is called a solution. So based on the physical state of solute and solvent, based on the physical state of solution, there are certain categorization done. All of you know that is explained in the initial portions of NCERT itself. The 9 combinations of solutions given in the table 2.1. 9 combinations of solutions given in the table 2.1, which you can find the 3 types of solution. The 3 types of solution, which is gaseous solution, liquid solution, solid solution, and based on the physical state of solute and solvent, 9 combinations. This you need to go through, particularly examples. Okay. So you can see gas in gas, liquid in gas, solid in gas, like that. Gas in liquid, liquid in liquid, solid in liquid, gas in solid, liquid in solid, solid in solid, like that. Mixture of oxygen, nitrogen, that is air, is an example for the first variety. Chloroform mixed with the nitrogen, second one. Camphor in nitrogen. There can be some eccentric examples which you must definitely gone through. That can be a question. Okay. So camphor in nitrogen gas can be taken as an example for solid dissolved in gas, like that. Oxygen dissolved in water, ethanol in water, glucose in water. Solution of hydrogen in palladium. Solution of hydrogen in palladium, which is explaining the catalytic activity of certain elements like palladium, nickel, etc. Amalgam of mercury. Various metals can dissolve in mercury. Amalgamation. Various metals except a few can dissolve in mercury. We call it as amalgams. Amalgams fall under the category liquid dissolved in solid. And various alloys stands for solid in solid. There are 9 combinations based on the physical state of solute and solvent, right? Can you tell me which is the most easily miscible combination? Among the 9, which is the most miscible combination? Yeah, no doubt. Gas in gas. Gas in gas combination will be easily miscible combination, right? So all these form homogeneous mixtures. We call it as solutions. One component will be called a solute and other component will be called a solvent. Only 2 components involved. We called a binary solution. In this chapter, we are mainly concentrating on binary solutions, right? Followed by in the NCERT, various concentration terms are explained. Various concentration terms. What are the important concentration terms that you must know? Various important concentration terms. Number one, mass percentage. Mass percentage. Mass of solute in 100 mass of solution. Mass of solute in 100 mass of solution. That is mass of solute by mass of solution into 100. This is mass percentage. Okay. Number two, volume percentage. Volume percentage. What is volume percentage? Volume of solute divided by volume of solution into 100. That is volume percentage. So mass percentage, volume percentage, mass volume percentage. Mass volume percentage. What is mass volume percentage? Mass of solute divided by volume of solution into 100. How many grams of solute in 100 ml solution? That is mass percentage. Okay, sorry, mass volume percentage. So mass percentage, volume percentage, mass volume percentage, right? Another important one is mole fraction. Mole fraction, designated by letter chi or simply X. What is mole fraction? Imagine you have a solution made up of component A and B. A having number of moles Na, B having number of moles Nb. Then mole fraction of A. All of you know what is mole fraction of A? Exactly. It is number of moles of A divided by number of moles of A plus number of moles of B. This is mole fraction of A. What is mole fraction of B? Mole fraction of B. It is Nb divided by Na plus Nb. That is mole fraction of B. And all of you know Xb is equal to 1 minus Xa. Sum of mole fractions is always unity. Sum of mole fractions is always unity. And any fraction like mole fraction doesn't have any unit. Okay. So mass percentage, volume percentage, mass volume percentage, mole fraction, a very important concentration term, molarity. Molarity. It is highly familiar to all. What is molarity? Fifth one, molarity, designated by capital M. What is molarity? Number of moles of solute in 1 liter solution. Number of moles of solute in 1 liter of solution. So number of moles of solute by volume of solution in liters called molarity. What is the unit of molarity? Exactly, mole per liter. That is a unit of molarity, right? And all of you know, suppose molarity M1, volume V1, number of moles is equal to M1 into V1, right? Number of moles is equal to molarity into volume in liters, right? Dilution equation known to all. What is dilution equation? Dilution formula. Suppose you are diluting a solution having molarity M1, volume V1. You are diluting by adding water. You get molarity M2, volume V2. What is dilution formula? M1 V1 is equal to M2 V2. Dilution formula. So before and after dilution, number of moles will be same. Before and after dilution, number of moles of solute will be same, because dilution process you are adding water, you are adding solvent. So it doesn't affect the number of moles of solute. What is the number of moles of solute? M into V. So M1 V1 before solute dilution is equal to M2 V2 after dilution. Right? Dilution formula. Similarly, when you are mixing two components of identical character, suppose you are taking solution 1 of HCl having molarity M1 volume V1, solution 2 of HCl having molarity M2 volume V2, and imagine you are mixing the two solution. Then what is the molarity of resultant mixture? M3 is equal to M1 V1 plus M2 V2 divided by V1 plus V2. Rather, in the denominator, it is final volume. Either you can take V1 plus V2, or in some of the numericals, it may be given a final different volume. So you have to use final volume. So M1 V1 plus M2 V2 by V1 plus V2, or final volume. That is additive formula when you are taking two identical solutions you are mixing. Suppose you are mixing an acid with alkali. Suppose you are taking HCl having M1 V1 mixed with NaOH having M2 V2. What is the resultant concentration? Then it depends on which is excess. There will be a neutralization reaction. Suppose acid is excess, then concentration M3, that is concentration of H plus, is equal to M1 V1 minus M2 V2 divided by V1 plus V2. When acid is excess, suppose alkali is excess, what do you do? Then the resultant concentration M3 will be concentration of OH minus. It will be M2 V2 minus M1 V1 divided by V1 plus V2. Understood? So these different kind of formula you may be encountering in various numericals, right? Similarly, there is another concentration term which is normality. Normality, another concentration term. Normality. Normality designated by capital N. Normality is number of gram equivalents. Number of gram equivalents of solute by volume of solution in liters. Number of gram equivalents of solute divided by volume of solution in liters. What is meant by gram equivalents? Gram equivalents is like number of moles. Number of gram equivalents is equal to weight by equivalent weight. All of you know number of moles is equal to weight by molar mass. Like that, number of gram equivalents is equal to weight by equivalent weight. What is meant by equivalent weight? Equivalent weight is equal to molar mass by n factor. What is n factor? N factor. I think many of you know what is meant by n factor. N factor. N factor for elements. N factor for elements, it is valency. N factor for compounds. N factor for compounds, it is the total positive or negative charge. N factor for acids, it is basicity. N factor for bases, it is acidicity. And N factor for redox reactions. N factor for redox reactions, it is the number of electron transferred. Number of electron transferred, a total number. For example, if you are dealing with the sodium, N factor equal to 1. If you are dealing with the calcium, N factor equal to 2. If you are dealing with a compound, say for example, aluminum oxide, Al2O3, it is 3 plus into 2 plus 6, or minus 2 into 3 minus 6. This is N factor, total positive or negative charge. Suppose you are dealing with acids. For example, HCl, hydrochloric acid, N factor equal to 1 as it is a monobasic acid. If you are dealing with sulfuric acid, the N factor equal to 2. If you are dealing with H3PO4, N factor equal to 3. So on. Right? For bases, it is the number of OH minus groups available. For redox reaction, total electron transfer. For example, if you are dealing with KMNO4 taken in acid medium, where it is converted to Mn2 plus, what is N factor? All of you know, it is plus 7 manganese changes to plus 2, N factor equal to 5. Right? Potassium dichromate, K2Cr2O7 converted to 2Cr3 plus in acid medium. It is 6 plus converted to 3 plus. N factor is 3 into 2 because there are 2 chromium. N factor equal to 6. Like that. So if you know the N factor, you get the equivalent mass. If you know the equivalent mass, you can find the number of equivalents. You can find the normality. That is what normality means, right? And normality can be related to molarity. Normality can be related to molarity for any substances. For example, hydrochloric acid. Suppose it is given 0.1 molar. It is 0.1 normality. Normality and molarity are same for hydrochloric acid because N factor is 1. Molar mass and equivalent mass are same. For hydrochloric acid, molar mass and equivalent mass are same. Therefore, molarity and normality are same. What about sulfuric acid? Suppose you are taking sulfuric acid, the N factor is equal to 2. Suppose molarity is 0.1, normality will be 0.1 into 2, that is 0.2. Right? So, normality value for any material, suppose any substance X having N factor N, suppose molarity equal to X, then normality will be N times X. N times X. Molarity and normality are so related. For any substance X, suppose N factor is given N, then molarity, if it is X, normality will be N times X, like that. For example, in this reaction, suppose molarity for KMnO4 given as 0.1, normality will be 0.1 into 5, that is 0.5, like that. Now, all formulae that we were applying in molarity, dilution formula, adding to acids, acid-base neutralization, or formula, you can apply the same way we were doing in molarity. What I mean is, various formula we applied for molarity. Dilution formula, M1V1 equal to M2V2. You can apply N1V1 equal to N2V2. M3 equal to M2V2 minus M1V1 by V1 plus V2. N2V2 minus N1V1. So the way you are using molarity formula, you can apply normality formula also. What is a unit of normality? What is a unit of normality? It is gram equivalent per liter. Gram equivalent per liter. That is normality. So understanding normality may be helpful for competitive exams many times. Is it clear? Now the next concentration term is molality. 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 Molality is small m. What is molality? Molality m is equal to number of moles of solute in 1 kilogram of solvent. The weight of solvent in kilogram. This is molality and the unit will be mole per kilogram. Mole per kilogram. Molality is number of moles of solute per kg of solvent. Number of moles of solute per kg of solvent. Okay, mole per kilogram. Molality, a highly used term in the concerned chapter. 2-3 major concentration terms that we use in the chapter is molality, mole fraction, etc. There is another one, ppm, parts per million. Parts per million. Parts per million. That will be weight of solute, quantity of solute in million quantity of solution. Right? So ppm can be understood as weight of solute. Weight of solute by weight of solution into million. That is ppm. Not necessarily it is weight by weight. It can be weight by weight of solution. It can be weight by weight of solvent. Because in this case, weight of solution and solvent is almost equal because quantity of solute is negligibly small. ppm we are using when the quantity of solute is trace amount in a solution. Hope you get the point. And ppm can be measured in mass by mass, mass by volume, volume by volume. Different way you can express ppm. One of the very famous unit of ppm is 1 ppm can be understood as 1 milligram per liter. This is one popular unit of ppm, or 1 microgram per ml. 1 microgram per ml. That is another important unit of ppm. So ppm can be expressed in different ways: mass by mass, mass by volume, etc. Okay, these are the important concentration terms that we encounter in the calculation purposes, numerical area, etc. Right? Once we finish that, the topic that we are going to discuss is solubility. Solubility of various solubility conditions. Solubility. Solubility. Capital S, solubility. It is nothing but the amount of solute that is dissolved in a definite amount of solvent or solution. That is solubility. Solubility can be expressed in different ways. Solubility can be expressed in gram per liter. Solubility can be in gram per liter. Solubility can be in milligram per liter. Solubility, that is what ppm is. Solubility can be gram per ml. Solubility can be mole per liter, that is molarity. There can be different way of expressing solubility. Different units we can make use, different concentration terms that we can make use in solubility. Right? What are the factors affecting solubility? That is another important point. What are the factors affecting solubility? Factors affecting solubility. The major factors that affecting solubility, number one is no doubt nature. Nature of what? Nature of the solute, nature of the solvent, nature of the solute and solvent. That's an important point. Like dissolves like. Many polar materials are dissolving in water. Water, it is called a universal solvent. It is able to dissolve many materials. That's why it is called a universal solvent. Anyway, dissolution depends on nature of matter. Certain substances cannot dissolve in water. Organic materials cannot dissolve in water. Paint cannot dissolve in water, all of you know. So solubility primarily depends on the nature, like dissolves like. So nature is an important point. Various other points are pressure. Pressure is an important point of solubility. Temperature. Temperature as an important point of solubility. Various parameters that affect the solubility. For example, when we discuss about temperature, how does the temperature influence solubility? How does temperature influences? That depends on the thermodynamic nature of the solution. Suppose a solution formation is endothermic reaction. Suppose a solution formation is exothermic reaction. The influence will be different. All of you know, endothermic reactions are favored at a high temperature. Exothermic reactions are favored at a low temperature. Suppose we are talking about solubility of quicklime, which is exothermic process. That is favorable at a low temperature. So quicklime dissolving to give lime water, it is highly favorable at a cool water, because it is favorable at a low temperature, because it is an exothermic process. Meanwhile, dissolution of sugar, it is favorable at a high temperature. It's better to see that sugar is easily dissolving in hot water. So temperature influence depends on the thermodynamic nature of the solution. There are certain salts whose dissolution occurs step by step in different thermodynamic way. In one step it is endothermic, in another step it is exothermic. It can be like that also. So it depends on the thermodynamic nature of the dissolution, which even can vary within the steps of dissolution. Okay. Anyway, endothermic dissolution favored at a high temperature, exothermic dissolution favored at a low temperature. Normally, pressure does not make an influence in the ordinary cases, but pressure has got a great influence in the solubility if you are discussing dissolution of gases in liquids. If we discuss about the dissolution of gases in liquid, pressure has got a great influence, and we need to go through in detail regarding the dissolution of gases in liquids. That is explained as Henry's law. You might have heard about or you may be remembering. Henry's law explaining solubility of gases in liquids. This is solubility of gases in liquids, which you can see with a simple diagram which is explained. With a simple diagram A and B, which you can see a gaseous matter dissolving in a given solvent. You can see there is a pressure applied, a matter kept here W1, a matter kept here W1, W2, W3. There is a greater pressure offered here. So you can see as the pressure applied over the surface of the solution increases, the dissolution increases. So here the dissolution will be less, here the dissolution will be more. That is explained as Henry's law. Henry's law explained in different ways. One of the statements that you can find for Henry's law is, there are different statements. One of the statements that you can find is this one. The solubility of gas in a liquid is directly proportional to the partial pressure of the gas present above the surface of the liquid or solution. So solubility directly proportional to partial pressure of the gas. Henry's law. There is another statement. You see that mole fraction of gas in the solution is proportional to partial pressure of the gas over the solution. All are identical statements. All are identical statements. Slight differences in the way it is presented. That's all. Okay. Another, the most commonly used form of Henry's law statement. The most commonly used form of Henry's law statement. This is the one. The partial pressure of the gas in the vapor phase is proportional to mole fraction of the gas in the solution. The partial pressure of the gas in the vapor phase is proportional to mole fraction of the gas in the solution. That is the most commonly encountered statement for Henry's law, with which we have the expression P equal to KH into X. The pressure, partial pressure, you see, partial pressure of the gas in vapor phase P proportional to mole fraction of the gas in the solution. P proportional to X and P is equal to KH into X. KH is called Henry's law constant. KH is called Henry's law constant. Hope you find a graphical representation over here. A graphical representation over here for finding the KH value of dissolution of HCl in cyclohexane. Over here you have partial pressure of HCl. Here you have mole fraction of HCl in the cyclohexane medium. So this is partial pressure of HCl. This is mole fraction of HCl in cyclohexane. You get a straight line starting from origin. So this is along the y-axis. This is along the x-axis. And slope of the line will be equal to KH. That is Henry's law constant. Henry's law constant depends on gases. For different gases, we can have different value of Henry's law constant. Greater the Henry's law constant, greater the Henry's law constant, lower will be the solubility of the gas. A gas with a higher Henry's law constant value found to be low soluble. It's very simple to understand. As this value increases, the solubility has to decrease. Right? Solubility X, the mole fraction, will decrease. So different gases have different KH values at the same temperature. And you can see a tabulated arrangement of KH values are given. A tabulated arrangement of KH values are available for various gases. You see, for helium, which is least soluble gas, all of you know, helium, hydrogen, etc. are very less soluble. You see their KH value. This is the KH value for helium, probably highest value in the table, 150 range, 145 range. That is the KH value for helium. So higher the KH value, lower the solubility. For hydrogen, 69. For nitrogen, you can see two different temperatures, KH values are given. What do you understand? When the temperature increases, KH value increases. That means solubility decreases. So dissolution of gases as a function of temperature, we can see as the temperature increases, dissolution decreases. I don't have to tell you, everybody agree. How do we prepare soda water? Is it in a hot water or cool water? For preparation of soda water, we prepare the preparation of soft drinks, preparation of soda water, we prefer ice cold water. Ice cold water, there is a great solubility of carbon dioxide in water during the preparation of carbonated drinks. Just because of the fact that when the temperature increases, we can explain theoretically, when the temperature increases, the KH value increases. 293, 76.48, 303, 88.84. Is it only for nitrogen? No, it's a general fact. You see for oxygen, 293, 34.86, 303, 46.83. So as the temperature increases, KH value increases and solubility will decrease. Clear? So which is the highly soluble component in the table? Which found to be highly soluble component in the table, you see a very low value, 1.83 into 10 power minus 5. A very low value of KH is available for formaldehyde, and that is found to be highly soluble as given in the table. Which is least soluble? The one with the high KH value, helium, is least soluble. So solubility of gases explained by Henry's law. That is a very important point to understand. Okay. And temperature dependence also. There are so many practical applications also commented. So many practical applications also commented for Henry's law and its application, which are quoted over here. As I said, preparation of soft drink, carbonated drink happens in the high pressure condition under low temperature. You see, to increase the solubility of CO2, the bottle is sealed under high pressure. Bottle is sealed under high pressure. There is another one explained, scuba divers. Scuba divers which are using the respiratory system. Usually, they make use of the ordinary air. Just imagine oxygen with nitrogen. But the greater quantity of nitrogen in the respiratory system causes many issues. What is the issue? The issue is nothing but as they go deep into the water where the pressure increases, the dissolution of nitrogen in the blood increases. Is there any problem? Naturally, there is no problem. Nitrogen is an inert gas. So the dissolution in the blood of nitrogen increases, no problem at all. But when they come back, what happens is when the pressure drops, the excess dissolved nitrogen will bubble out. They will come out. So excess dissolved nitrogen from the blood, when bubble out, it creates a highly painful situation. We call it as bends. It is called bends. It is highly painful. And sometimes it is risky also. So to avoid bending character or bends, what we do is the respiratory oxygen is diluted with helium. It is diluted with helium. You see what we do? It is sufficiently diluted with helium to avoid bends as well as the toxic effect of high concentration of nitrogen in the blood. The tanks used by scuba divers are filled with air diluted with helium, 11.7% helium, and a percentage of nitrogen which is in the range of 70, we reduce it to 56.2 and oxygen 32%. That way we maintain. So we dilute with helium. Right? Nitrogen is inert, helium is also inert, but the solubility of helium is very low. Unlike nitrogen, solubility of helium is very low. So diluting with the helium, it will be helpful to avoid the excess dissolution of nitrogen in the blood. So it's an application of Henry's law. And there is one more point explained, anoxia. What is anoxia? At high altitudes, the partial pressure of oxygen is less than that at the ground level. This leads to low concentration of oxygen in the blood and tissues of people living at a high altitude and even climbers. And they, it's creating a situation like they are unable to think properly. They are unable to think properly due to less dissolved oxygen content in the blood. The phenomenon called anoxia. Anoxia. All these are related to pressure conditions. So when the pressure drops, the amount of oxygen dissolved in the blood also drops. That creates a situation called anoxia. So like this, different applications of Henry's law also explained there. Okay. After this, we are switching on to a term, vapor pressure. Vapor pressure. What is meant by vapor pressure? All of you know what is vapor pressure? Vapor pressure is nothing but the pressure offered by the vapors over the surface of the liquid. The pressure offered by vapors over the surface of the liquid. Okay. Suppose you have a solvent. This is the top layer molecules of the solvent. This is the top layer molecules of the solvent. I don't have to tell you, there will be a natural evaporation. The surface molecules will try to make itself free. So there will be a natural evaporation, and imagine it is kept in a bell jar system with a closed container, closed system like this with a bell jar. You can see the vapors will be accumulating over here, and ultimately it comes to a state of equilibrium. The condensation and evaporation comes to a state of equilibrium. At that condition, the pressure offered by vapor particles over the surface of the liquid, that is called equilibrium vapor pressure. Equilibrium vapor pressure. So initially there is evaporation. After some time, condensation starts, ultimately attains a state of equilibrium. Right? At that condition, the pressure offered by the vapor particles over the surface of the liquid is called vapor pressure. How this vapor pressure related to boiling point of the liquid? All of you know. What is boiling point? Boiling point is the temperature at which vapor pressure of liquid becomes equal to external pressure. What are the factors depends or influencing vapor pressure? What are the factors? Factors affecting vapor pressure. Factors affecting vapor pressure. No doubt. Number one is nature. Different materials are having different degree of evaporation. There are materials which are volatile and non-volatile. Volatile materials are easily evaporating, while non-volatile materials are less evaporating. Do you understand? So, volatile materials means their evaporation will be larger, vapor pressure will be larger, their vapor pressure becomes equal to external pressure very fast, their boiling point will be lower. Higher the vapor pressure means boiling point is lower. So volatile materials are high vapor pressure and the boiling point is low boiling in nature. What about non-volatile materials? Their vapor pressure is low, their boiling point is high. So vapor pressure and boiling point are inversely related. Is it clear? Now what are the other factors influencing vapor pressure? No doubt, temperature is an important factor influencing vapor pressure. Temperature. As the temperature increases, vapor pressure increases. If you take a sample of water kept at 25 degrees Celsius, as the temperature increases, 25, 30, 40, 50, like that, the vapor pressure keep on increasing. And at a temperature 100 degrees Celsius, the vapor pressure of liquid water becomes equal to external pressure, and at that temperature, water boils, and we call it as boiling point. So what is the boiling point? The temperature at which vapor pressure of a liquid becomes equal to external pressure. At 100 degrees Celsius, vapor pressure of water becomes equal to external pressure and it starts boiling. So each and every material, each and every liquid, the boiling point is decided by its volatile nature and it is decided by the vapor pressure. Okay, vapor pressure decided by the nature of the material as well as the temperature increases, vapor pressure increases. Once the vapor pressure becomes equal to external pressure, the liquid starts boiling. Okay, Now, what about some solute is added to this, particularly a non-volatile solute? What about when a solute is added to this? This is pure solvent. This is pure solvent. Suppose we are taking a solution. Suppose we are taking a solution. You can see the top layer surface particles. It may not be solvent alone. It will be solute plus solvent. There will be alternate particles will be solute particles. You see that? Earlier, the top layer molecules was fully solvent molecules. Now, there is solute particles also. So, what will be the result? Suppose the solute particles is a non-volatile solute. What will be the result? See, the surface area of the solvent molecules increases, and you can see as a consequence of which, when the surface area increases, the molecules evaporating will decrease. When the surface area, here, the entire surface is solvent molecules. Here, the surface molecules are alternate solvent and solute. Some of the surface molecules are solvent molecules replaced by solute particles. So, what happens? The surface area of solvent molecules decreases. So, solvent molecules in the surface decreases. Evaporation will decrease. Here, the evaporation like this. Here, the evaporation can be like this. The amount of vapor particles will decrease. Vapor pressure will decrease. This is what we are learning as a colligative property, lowering of vapor pressure. So, when you add a non-volatile solute, suppose there is A and B, A the solvent and B non-volatile solute. When a non-volatile solute is added to a solution, preparing a solution, you can see the vapor pressure drops. When the vapor pressure drops, quite naturally boiling point will increase. This is what we are learning as colligative properties, right? While the contribution of vapor pressure, contribution of pressure contribution in a solution can be explained by another law that is called Raoult's law. That is called Raoult's law. The next is Raoult's law. Raoult's law states that suppose in a solution there are two components A and B. Imagine both are volatile components, two components in a solution, binary solution A and B, right? Containing A, the number of moles of A, Na, number of moles of B, Nb. Just imagine. Raoult's law states that the vapor pressure contribution of one component will be directly proportional to its mole fraction in the solution. That is Pa proportional to Xa. This is Raoult's law. Vapor pressure contribution of one component will be directly proportional to mole fraction of that component in the solution. So, Pa means vapor pressure contribution of component A. Xa means mole fraction of A, all of you know, Na by Na plus Nb. So, Pa proportional to Xa and Pa equal to P naught A into Xa. What is this P naught A? P naught A means, all of you know, I believe, it is vapor pressure of pure A. Suppose A taken along, pure. Then the vapor pressure of A under the identical condition is called P naught A. So, this is vapor pressure contribution of A in the solution. This is vapor pressure of pure A, and this is mole fraction of A in the solution. Similarly, you can write Pb proportional to Xb, and Pb is equal to P naught B into Xb. This is what Raoult's law, right? Then what is the P total? That is P solution. P solution, that is P total is equal to Pa plus Pb. That is equal to P naught A Xa plus P naught B Xb. And you've been able to manipulate the formula in different way. As all of you know, Xa can be written as 1 minus Xb like that. So different manipulations are possible, and based on which you can expect questions also. This is what Raoult's law. And any solution which obeys Raoult's law will be called a ideal solution. All of you know what are ideal and a non-ideal solution. That is the next topic. Ideal solution, non-ideal solution. Ideal and non-ideal solution. What is meant by ideal solution? Ideal solution means the one which obeys Raoult's law. The one which obeys Raoult's law. What is Raoult's law? PE equal to P naught A XB, XA, or PB equal to P naught B XB. That is Raoult's law. Partial pressure of a component will be equal to vapor pressure of pure component into mole fraction of that component in the solution. That is Raoult's law. So any solution which obeys Raoult's law, it will be called a ideal solution. What about a non-ideal solution? Non-ideal solution, PA not equal to P naught A XA. So here it obeys Raoult's law, here it does not obey Raoult's law. PA will not be equal to P naught A XA. Either it is going to be greater than or less than. There will be two characteristics for non-ideal solution. All of you know non-ideal solution will be the one with the positive deviation and the one with the negative deviation. What about positive deviation? For positive deviation, PA will be greater than P naught A XA. Here PA equal to P naught A XA, ideal solution. PA greater than P naught A XA, that is non-ideal solution, positive deviation. Then what about negative deviation? It is PA less than P naught A XA. So this is ideal solution, this is non-ideal positive deviation, and this is non-ideal negative deviation. Right? Is that all? No, there are more conditions. Hope all of you remember. Enthalpy of solution, second one. Enthalpy of solution, enthalpy of mixing, it will be 0. It is neither exothermic nor endothermic. During mixing of A and B, there is no heat change. That is ideal solution. What about non-ideal positive? Delta H mixing will be greater than 0. That means it is positive. That means it is endothermic in nature. What about negative deviation? It is delta H mixing. It will be less than 0. That is negative. Negative means exothermic reaction. So for ideal solution, there is no change in enthalpy during mixing. Non-ideal solution, positive deviation. It is delta H positive, non-ideal solution negative deviation, delta H negative. Okay, not over. Third one, delta S mixing or delta V mixing, delta V mixing is equal to 0. There is not going to be any change in volume during mixing. Suppose you mix 10 liters of A with 10 liters of B, you get exactly 20 liter. That is ideal solution. What about non-ideal positive? Non-ideal positive, it will be delta V mixing is greater than 0. That means volume mixing increases. 10 liter A mixed with 10 liter B, you are going to get 20 plus. If you get exactly 20, ideal. 20 plus, non-ideal positive. 20 less than 20, non-ideal negative deviation. For negative deviation, delta V mixing will be less than 0. Okay, for all these cases, the characteristics will be like this. For ideal solution, AB molecular interaction is similar to AA molecular interaction and BB molecular interaction. So the molecular interactions before mixing and after mixing will be almost the same for ideal solution. If you mix identical substances, benzene, toluene, normal hexane, normal heptane, chloroethane, bromoethane, like that, identical charactered molecules if you are mixing. Before and after mixing, the molecular interaction is almost same. Therefore, there is no change in enthalpy. There is no change in volume. If you take 10 liter A mixed with 10 liter B, volume will remain 20 liter, 10 plus 10. Hope you understand. There is no change in volume. There is no increase or decrease in volume. Right? What about non-ideal positive deviation? It is found that AB interaction is much less than AA and BB interaction. That means after mixing, the molecular interaction decreases. AB interaction less. What does that mean? After mixing, AB interaction, molecular interaction decreases. So before mixing, molecules were very close. After mixing, their interaction decreases. They come apart. So there will be an increase in volume. 10 liter A plus 10 liter B not necessarily give you 20 liter. It may be 20 plus liters. A strong attractive force is decreasing, minimized. That means a strong bond is broken. Means energy is absorbed. Endothermic process. Hope you get the picture. Molecules were very close. Now they are far apart. They can easily evaporate. Therefore, vapor pressure increases. Vapor pressure is more than what you expect theoretically. Because after mixing, molecular attraction decreases. Hope you get the picture. What about negative deviation? Just opposite. AB interaction is much greater than AA and BB interaction. After mixing, molecular attraction increases. Before mixing, molecules were far apart. After mixing, they come very close. So after mixing, attractive force increases. A strong bond is formed. So heat is liberated, exothermic. The molecules are coming close, means volume decreases. 10 liter A, 10 liter B, when mixed, you get less than 20 liters. After mixing, molecular attraction increases. So evaporation decreases. Vapor pressure decreases than the theoretical figure. This is what ideal, non-ideal, positive, negative. For ideal, molecular attraction before and after mixing are same. It seems to be following Raoult's law. Non-ideal, positive, after mixing, molecular attraction decreases. After mixing, molecular attraction increases. That is non-ideal, negative deviation. If you represent graphically, I am sure you might have seen in the textbooks, representing graphically the ideal, non-ideal solutions. This is ideal solution. Taking mole fraction along the x-axis and vapor pressure along the y-axis. This is XA equal to 0 and XA equal to 1. That means from left to right, A increases. Now here XB equal to 0 and here XB equal to 1. That means from right to left, B increases. So from left to right, A increases. From right to left, B increases. This is pure A and this is pure B. This is pure B area and this is pure A area. From left to right, A increases. From right to left, B increases. So how is going to be the graph? How is going to be the graph? According to Raoult's law, as A increases, vapor pressure increases. And what is this point? At this point, XA equal to 1. When XA equal to 1, PA equal to P naught A. So this is P naught A. And this is the graph for PA. Right? What about B graph? B graph, a similar graph you can find. B graph, a similar graph you can find. This is PB graph. This is PB graph from right to left. the quantity of B increases. So this is PB graph. I don't have to tell you, this is P naught B. And this will give you the resultant. This is P total equal to PA plus PB. This is what ideal solution represented by Raoult's law. I repeat, from this point to this, A increases. As A increases, PA increases and reaches the maximum when XA equal to 1, PA equal to P naught A. This is pure component A. And this is vapor pressure of pure component A, already commented. From right to left, B increases. Quite naturally, it is. See, the nature of the graph also, not necessarily the graph is coming like the way I have drawn. From the graph, you can understand the way I have drawn in this example. B is more volatile than A, that's all. This is B more volatile than A. Suppose A more volatile than B, the graph would have been coming like this. Nature of the graph, it may come like this, like this, like this. That depends on the nature of the liquid A and B. Hope you get it. This is ideal solution. What about non-ideal solution, positive deviation? Non-ideal solution, positive deviation. How is going to be the graph? How will be the graph represented? Non-ideal, positive deviation. Very simple to understand. Very, very simple to understand. PA is not going to be a straight line. It is greater than the theoretical data. That means PA will be like this. There will be a positive deviation. What about PB? There will be a positive deviation. What about P total? There will be a positive deviation. This is non-ideal solution, positive deviation. I hope you get the picture. So this is straight line ideal. This is positive deviation, non-ideal. Okay. This is ideal, and this is non-ideal, positive deviation. What about non-ideal, negative deviation? Non-ideal, negative deviation. How is going to be that? This is non-ideal, negative deviation. It will be, this is ideal, this is ideal. This is non-ideal, negative deviation. This is non-ideal, negative deviation. And this is non-ideal, negative deviation. All you can find there is a decrease, because the molecular attraction as increases, the vapor pressure will decrease. So pressure contribution decreases from the ideal character. That is non-ideal, negative deviation. That is about Raoult's law, ideal solution, non-ideal solution. Right? Various examples that are quoted in the materials and NCERT, few examples are available. You need to go through and by heart it. Okay? Very important topic. Right? Now, the same Raoult's law which we were commenting here, two components A and B. Two components A and B. Imagine we have a solution where we have a solvent A. A is a solvent, and that is added with a solute B, which is a non-volatile solute. Just imagine, non-volatile solute B added to form a solution, and thereby you prepare a solution. You have a solvent A added with a non-volatile solute B. What will be the characteristic nature? Let's understand. The total pressure of the solution, P solution, is equal to PA plus PB, isn't it? Okay. Now, that becomes approximately equal to PA. Why? Why? Because PB, B is a non-volatile component. Non-volatile component will have a very low evaporation tendency. So the vapor pressure contribution by B will be negligible. So what happens? You get PS is equal to PA plus PB will become PA. So P solution is equal to PA. That is equal to P naught A XA. And that is equal to P naught A into 1 minus XB. XA can be written as 1 minus XB. So what do you get? PS is equal to P naught A minus P naught A XB. Now rearrange. Upon rearranging, you will be able to get P naught A minus PS divided by P naught A is equal to XB. You will get it like this. Upon rearranging, very simple rearrangement, you will get P naught A minus PS divided by P naught A is equal to XB. This is vapor pressure of pure solvent. This is vapor pressure of solution. And this is vapor pressure of pure solvent. All of you know, this is XB, mole fraction of non-volatile solute. I am sure all of you understand the numerator part. The numerator part, this much. It is called a delta P, called a lowering of vapor pressure. Lowering of vapor pressure. Whenever you add a non-volatile solute into a solvent, the vapor pressure of solvent will decrease because the solute is non-volatile. It has got a reluctance towards evaporation. So vapor pressure will decrease. And that is what we are learning as colligative properties, which is followed by. So this is called a lowering of vapor pressure, delta P. Delta P is equal to P naught minus PS. While the entire term is called a relative lowering of vapor pressure. This entire term will be called as relative lowering of vapor pressure. Relative lowering of vapor pressure. The entire term, that is P naught minus P naught A minus PS by P naught A will be called relative lowering of vapor pressure. That is another way you can express the law. The relative lowering of vapor pressure is equal to mole fraction of non-volatile solute. Relative lowering of vapor pressure is mole fraction of non-volatile solute, and this is the one of the most important colligative property we learn. What is meant by colligative property? What is meant by colligative property? The most important topic from the chapter, colligative properties. Colligative properties. Colligative properties means all of you know those properties of a dilute solution which depends on the number of solute particles, the amount of solute particles present, not on the nature of the solution. And there are four important colligative properties we learn. Number one, relative lowering of vapor pressure. That is delta P by P naught. This is number one. Number two, elevation in boiling point. Elevation in boiling point, delta TB. Number three, depression in freezing point. Depression in freezing point, delta TF. And number four, osmotic pressure. Osmotic pressure represented as pi. These are the four important colligative properties, and we are referring the number one colligative property, that is relative lowering of vapor pressure. Lowering of vapor pressure depends on the amount of non-volatile solute present, not on the nature of the solution. That is evident from the formula. So colligative property number one will be this only, delta P by P naught equal to XB, or in detail P naught minus P naught minus PS by P naught equal to XB, right? Or you can expand that for finding the molar mass of non-volatile solute. That is one of the most important application of colligative property. It is used for finding the molecular mass of unknown non-volatile solutes. How it can be calculated? P naught minus Ps by P naught equal to NB by NA plus NB, that is WB by MB divided by WA by MA plus WB by MB. Or even you can approximate as this quantity, if it is negligible, you can take it as NB by NA, that is WB by MB, WA by MA. This way also you can approximate as the quantity of solute if it is negligible. If suppose you are dealing with a dilute solution where the quantity of solute is negligible compared to solvent, you can make use like that also. Okay. So experimentally, if you determine this, there are experimental instruments available, the experiments available for determining the relative lowering of vapor pressure. Ostwald-Wacker method. Ostwald-Wacker method we are not learning in the syllabus content. It is experimental investigation study to find the relative lowering of vapor pressure. This value we can determine. And now this value you can note down. This is a non-value. And this value you can note down. You can calculate what is the molar mass of unknown solute. So determination of molar mass can be done by colligative property. And number one colligative property, lowering of vapor pressure. What is lowering of vapor pressure? When you add a non-volatile solute into a solvent, the vapor pressure of solvent depressed or suppressed. There is a lowering in vapor pressure. And that lowering in vapor pressure is directly related to quantity of solute added. And that is what explained so far. Now the next one is elevation in boiling point. Second colligative property, elevation in boiling point. Represented by delta TB, elevation in boiling point. I am sure all of you understand what is boiling point. Boiling point is the temperature at which vapor pressure of a liquid becomes equal to external pressure. That is boiling point. Suppose graphically if we represent, this is vapor pressure along the y-axis and temperature along the x-axis. And imagine this is external pressure, P external, for example 1 atm in case of atmospheric pressure. And you see a solvent. A solvent, the graph will be like this. This is a pure solvent. Just imagine, pure solvent. And you see as the temperature increases, vapor pressure increases. At this particular point, the liquid starts boiling, T1. For example, water, T1 will be 100 degrees Celsius, all of you know. As the temperature increases, vapor pressure increases, and at a particular temperature, vapor pressure becomes equal to external pressure, and that is the boiling point. Suppose to this solvent, we are adding a non-volatile solute. Imagine we are adding a non-volatile solute. What will happen? The new graph could be like this. This could be the new graph. And this could be the new boiling point T2. This is solution. Why? Because as you add a non-volatile solute, there will be a lowering of vapor pressure. So upon addition of a non-volatile solute, vapor pressure decreases. So the new graph will be below the old graph. So the new boiling point will be after the old boiling point. There is a elevation in boiling point. This is elevation in boiling point. So that elevation in boiling point delta TB is directly proportional to delta P. This is delta P. So this is directly related to this. And that is directly related to amount of solute. It depends on the amount of non-volatile solute added. More you add non-volatile solute, more will be lowering of vapor pressure, more will be elevation and boiling point. Hope you get the picture. So we can relate delta TB proportional to molality. Molality is a concentration term. And all of you know concentration term refers amount of solute in a solution. A comfortable concentration unit used is molality, as it is temperature independent, and more or less it is same as molarity. But molarity is temperature dependent. So some advantages, experimental advantages over using molality. That's all. Okay. So delta TB proportional to M molality, and delta TB is equal to a constant Kb into molality, where Kb is called a molal elevation constant. Molal elevation constant, also called a ebullioscopic constant. Ebullioscopic constant. Molal elevation constant, ebullioscopic constant. Delta TB is equal to Kb into M. How do we define Kb? Delta TB equal to Kb when M equal to 1. That is the way you define the constant. It is the elevation in boiling point. Kb is defined as elevation in boiling point offered by a unimolar solution. It depends on the solvent. For each solvent, there is a Kb value. How do you define that? It is the elevation in boiling point shown by unimolar solution. For water, Kb value is Kb value for water. It is 0.52 Kelvin per molar. That is 0.52 Kelvin kilogram per mole. That is the unit. And there is a tabulated information of various Kb data for different solvents, which you can just go through to identify which is maximum, which is minimum, which is second, which is third, like that, to get a relative idea, not to by heart the data. Okay. Even this colligative property we can use for finding the molar mass of unknown solute. How is that? Delta TB is equal to Kb into M. That is equal to Kb into mass of solute into 1000 by molar mass of solute into mass of solvent in gram. This is nothing but molality, detail explained. That's all. Now, what is Mb? What is the molar mass of unknown solute? It will be Kb into weight of solute into 1000 divided by delta TB into weight of solvent in gram. So what all things you must note down to find out the molar mass of non-volatile unknown solute? You must know which is the solvent, thereby which is what is Kb. You must note down the weight of the solute that you used to prepare the solution. You must find out delta TB. Delta TB can be calculated by using Beckmann's thermometer, which is used for finding small difference in the temperature. Anaerobic thermometer, Beckmann's thermometer, can be used for determining delta TB, and weight of solvent also you can note down. You can find out Mb. That is elevation in boiling point. Colligative property number 2. Number 1, lowering of vapor pressure. Number 2, elevation in boiling point. Number 3, depression in freezing point. Number 3, depression in freezing point. Designated as delta TF. Delta TF, depression in freezing point. Once again, what is freezing point? All of you know, freezing point means the temperature at which vapor pressure of solid phase and liquid phase meet. That is freezing point. At 0 degrees Celsius, the vapor pressure of ice and water will be equal. That is freezing point of water. So we can represent graphically what is the freezing point. Vapor pressure versus temperature. freezing point of water, say for example, it could be understood like this. This is ice, just imagine, that is solid phase, and this is liquid water. This is liquid water in the liquid phase, just imagine, or solvent and solvent in the respective phases. Solvent, liquid phase and solid phase. This is the point which is called the freezing point. This is T1, freezing point. For example, water, it is 0 degrees Celsius. All of you know. Okay. Now, to this water, imagine we are adding sugar. Imagine you are adding urea. Imagine you are adding glucose. Imagine you are adding any of the non-volatile solute. What will be the new graph? The new graph will be like this. By like this, there will be a lowering of vapor pressure. This is solution. This is solution. According to the quantity of sugar that you add, according to the quantity of non-volatile solute that you add, vapor pressure will be decreasing. And the new graph will go like this. And this is the new freezing point, T2. And the freezing point is depressed. This is delta TF. New freezing point, depression in freezing point, depression in freezing point, right? Once again, that depression in freezing point, so if this is 0 degrees Celsius, this can be some negative temperature. It finds wide application, you might have heard about. In cold regions, the water used in car radiators mixed with the antifreeze components. It is added with antifreeze components in order to suppress the freezing point of water. Otherwise, it will freeze. Under normal conditions where the temperature go to negative side, the water will freeze, and that will create damages to the systems, automobile systems, radiators, cooling systems, and all. So we are adding antifreeze components like glycerin, glycol. Normally, we are adding glycol. Glycol used as an antifreeze component so that the freezing point is suppressed. Hope you get the picture. Once again, this delta TF is proportional to delta P, which is proportional to amount of solute, colligative property. So we conclude delta TF is proportional to molality, which is a concentration term, and delta TF is equal to a constant Kf into molality, where Kf is called a molal depression constant. Molal depression constant, also called a cryoscopic constant. Cryoscopic constant depends on the nature of the solvent. Different solvents having different Kf value, and it can be defined in the same way we did earlier. Delta TF is equal to Kf when m equal to 1. So what is the definition? Delta Kf is defined as the depression in freezing point caused by a unimolar solution. For water, Kf value is 1.86 Kelvin kilogram per mole. Different solvents will have different Kf value. And once again, this can be used for finding the molecular mass of unknown solute. How is that possible? Same way, dicto. Delta TF is equal to Kf into weight of solute into 1000 divided by molar mass of solute into weight of solvent, from which you can find out what is molar mass. Molar mass is equal to Kf into weight of solute into 1000 divided by delta TF into weight of solvent in gram. Dicto explanation the way we have seen in the previous case. There it is elevation in boiling point. Here it is depression in freezing point. Right? So upon addition of non-volatile solute, vapor pressure will decrease. Boiling point will increase. Freezing point will decrease. Hope you get it, right? And two more important things you must know is thermodynamic relation for Kf, Kb. Kf, Kb, Kf versus thermodynamic relation, that is delta H. That's a very important point. See, the relation is Kb is equal to RTB square by 1000 LV. Kb is equal to RTB square divided by 1000 LV. R is gas constant, TB is boiling point. This is boiling point. And LV, latent heat of vaporization. Latent heat of vaporization, which will be delta H by molar mass. Delta H vaporization by molar mass. Therefore, it is Kb is equal to RTB square M divided by 1000 delta H vaporization. This is a thermodynamic relationship connecting Kb versus delta H. Similarly, you can have Kf versus delta H. How is that? Kf is equal to RTF square divided by 1000 LF, where LF is latent heat of fusion. This is gas constant, this is freezing temperature, this is latent heat of fusion. And that comes again as Kf is equal to RTF square M divided by 1000 delta H fusion. So please review all these formula as a revision part. Remembering the formula, there can be numerical problems based on this, or straight down it can be a question like formula question. Okay, that's all about the various terms related to three colligative properties: lowering of vapor pressure, elevation and boiling point, depression and freezing point, and Kf, Kb data versus enthalpy. The last one is most important property, osmotic pressure. Osmotic pressure. Osmotic pressure. All of you know what is osmosis and osmotic pressure. If you take a solution, imagine I'm telling an experiment. If you take a solution taken in an inverted funnel, the mouth of which is closed with a semi-permeable membrane. This is a semi-permeable membrane. And the funnel is taken with a solution inside it. And the entire funnel is immersed into a solvent. Imagine it is immersed into a solvent. So this is solution and this is solvent. This is solvent. So we are taking an inverted funnel, the mouth of which is closed using a semi-permeable membrane. What is a semi-permeable membrane? All of you know. It permits the flow of solvent molecules, not the solute particles. Example, copper ferrocyanide, an artificial, famous, popular semi-permeable membrane. Now, that is blocked, the mouth of the funnel is blocked with that, and we are taking a solution in that funnel and is immersed into a suitable solvent. We know what will happen. The water molecules, the solvent molecules start entering into the solution through the semi-permeable membrane, and the level of the solution gradually increases. The level of the solution gradually increases, finally come to a equilibrium state. At that equilibrium condition, the hydrostatic pressure offered by the solution, which prevent the further flow of solvent molecules, is called osmotic pressure. Initially, the level will rise. After some time, the level come and stand somewhere here, right? And it attain a state of equilibrium. Why? Why such a state of equilibrium? Now, the hydrostatic pressure offered by the solution, prevent the net flow of water molecule into the solution through osmosis, or as many water molecules now enter at equilibrium will be leaving from the solution. It attain a state of equilibrium. At that equilibrium, pressure offered by the solution is called osmotic pressure. So osmotic pressure is defined as the equilibrium pressure offered by the solution which prevent the net flow of solvent molecules into the solution through osmosis. That is osmotic pressure. It has been well explained by Van Hoff explained or studied the theory of dilute solution content based on which, and he was able to explain the osmotic pressure pi is proportional to 1 by V. It is inversely related to volume of the solution. Van Hoff Boyle's law. It is directly proportional to temperature. Van Hoff Charles law. This is Van Hoff Boyle's law. Van Hoff Boyle's law. All of you know what is Boyle's law. Pressure of a gas is inversely proportional to volume. The pressure of a given mass of gas is inversely proportional to volume at a constant temperature. Same is Van Hoff Boyle's law. The osmotic pressure of solution is inversely proportional to volume at a given temperature. Van Hoff Charles law. The pressure is directly proportional to absolute temperature, provided the volume is fixed, right? And Avogadro's law, pi proportional to n, Van Hoff Avogadro's law, and thereby the consolidation of the formula happens pi proportional to nt by v, or pi v proportional to nt, pi v is equal to nRT, where R is the universal gas constant. Here is called a universal solution constant, numerically same. Numerically the value found figured to be same. Pi V is equal to nRT, where pi is osmotic pressure, V is the volume of the solution, N the number of moles, R is solution constant, and T is temperature. Or you can write pi is equal to N by VRT, or pi is equal to CRT or MRT. C is concentration. Pi is equal to concentration into RT. That is osmotic pressure and the related topics. And a very important topic, all of you remember, isotonic solution. What is isotonic solution? Isotonic means two solutions having same osmotic pressure. That is isotonic solution. Two solutions having same osmotic pressure is called a isotonic solution. We are learning the applications also. The intravenous injections are salinated sufficiently such that it is isotonic with the blood. Otherwise, what will happen? Suppose it is hypertonic. Water from the RBC will come out and RBC will shrink. Suppose it is hypotonic. Water from the medicine will enter into RBC. RBC will swell and ultimately may burst. Both are dangerous. Highly risky. Sometimes we may lose the life. It is dangerous. Sometimes death may occur. All of you know this. So, intravenous injections that are given directly to the blood are made sufficiently salinated that it is isotonic with the blood. What is isotonic? Two solutions having same osmotic pressure. That means C1RT is equal to C2RT at the same temperature. That is C1 equal to C2. That is N1 by V is equal to N2 by V if the volume is same. That is N1 is equal to N2. That is isotonic. Okay, so the solution with a higher osmotic pressure, more concentrated, that is hypertonic solution. Less concentrated, dilute one, that is hypotonic solution. All these topics related to osmotic pressure, very, very important. A topic on reverse osmosis, a topic on reverse osmosis. I hope all of you remember that reverse osmosis, which is used for the desalination plants. It is used for desalination plants. The diagrams are available. These are osmotic pressure experiment and related conditions. This is desalination application, desalination plant applying RO, reverse osmosis, where you find two chambers, one fresh water, salt water, separated by a semi-permeable membrane, and here there is a piston cylinder arrangement. We are applying a pressure greater than osmotic pressure. When you apply a pressure greater than osmotic pressure, actually the water is entering from here to here. Actually, by osmosis, water will be entering from this chamber to this chamber. But here, what is going to happen is, we are applying a pressure greater than osmotic pressure. Usually, water is entering this way. But when you do this, water is entering this way. And fresh water can be taken out. Reverse osmosis. By applying a pressure greater than osmotic pressure, water will start migrate from a solution to the fresh water area. That is reverse osmosis, the basic principles of desalination plants. Okay. And finally, a talk on abnormal colligative properties. Abnormal colligative properties. That is the final topic to be discussed. Abnormal colligative properties. Many times when you observe colligative properties, we find there are some abnormalities. That abnormalities may arise due to two reasons. One is called dissociation. Abnormality arises due to dissociation. That is happening with electrolytes. And one is due to association. So dissociation and association, the reason for abnormal colligative properties. For example, if you take NaCl, and if you are talking about 1 lakh particles of NaCl, all of us know NaCl will split into Na plus and Cl minus. 1 lakh NaCl will split into 1 lakh Na plus, 1 lakh Cl minus. Each one act as a solute particles. So effectively there are 2 lakh particles. Colligative properties will be much higher than what we expect. Molar mass will be much lower than what we expect. Actual molar mass is 58.5, 60 range. What we get will be in the range of 30. Because each particle split into Na plus Cl minus. So there will be abnormality in colligative property. Remember, colligative property depends on the number of solute particles. We are taking 1 lakh NaCl. Effective particle will be 1 lakh this, 1 lakh this, 2 lakhs. Sometimes you know what can happen. For example, acetic acid taken in benzene. Acetic acid taken in benzene. Acetic acid taken in benzene will undergo dimerization. Two acetic acid molecule will undergo dimerization. They will act like a single particle. The two acetic acid molecule will act like a single particle, like this. It undergo association. Imagine we have taken 2 lakhs molecules. Imagine we have taken 2 lakhs molecules. This act as a single entity. You get 1 lakh molecules. So number of molecules decreases. Number of particle decreases because they undergo association. So the colligative property will decrease. Molar mass will increase. This is what abnormality observed due to dissociation, due to association. It is corrected by introducing a term by Van Hoff known as Van Hoff factor. He has corrected the abnormalities by introducing Van Hoff factor. It is called Van Hoff factor, represented as I. Van Hoff factor I. What is I? Van der factor I is equal to you can figure out here, this is Van der factor I, normal molar mass divided by abnormal molar mass. I is equal to normal molar mass divided by abnormal molar mass. What is the normal molar mass of NaCl? 60 range, 58.5. Abnormal value will be 30 range. So 60 by 30, I factor will come as 2. For dissociation, I factor will be greater than 1. What about association? I factor will be less than 1. Okay. Now, I factor is equal to normal molar mass by abnormal molar mass, or observed colligative property divided by calculated colligative property. I is equal to normal molar mass by abnormal molar mass, observed colligative property divided by calculated colligative property, or I is equal to total number of molecules or particles after association or dissociation divided by total number of moles of particles before association or dissociation. So three terminologies represented for I factor. What are the three terminologies? Normal molar mass by abnormal molar mass, observed colligative property by calculated colligative property, total number of particles after association dissociation divided by total number of particles before association dissociation. This is I factor. I factor is introduced into all colligative properties. I factor is introduced into all colligative properties. Delta P by P naught equal to XB becomes I into XB. Delta TB equal to KB into M becomes I into KB into M. Delta TF equal to KF into M becomes I into KF into M. Pi equal to CRT becomes I into CRT. All colligative property introduced with the I factor. If there is no abnormality, ideal solution, I will be 1. For ideal solution, I is equal to 1. For dissociation, I is greater than 1. For association, I is less than 1. And it also depends on the degree of dissociation and association. It also depends on degree of dissociation and association. Please keep it in mind. Please keep it in mind. For dissociation, alpha degree of dissociation equal to I minus 1 by n minus 1. What is n? N for NaCl 2, n for CaCl 2 3, n for AlCl 3 4, n for SnCl 4 5. It is the number of ions after dissociating. NaCl, Na plus Cl minus 2, CaCl 2, Ca plus 2Cl minus 3, AlCl 3, aluminum plus 3Cl 4, like that. So that's an important formula, don't forget, applied for various numericals. Alpha degree of dissociation is equal to Van der factor I minus 1 by n minus 1. Also keep it in mind. When alpha is 100%, I is equal to n. I am talking about dissociation. That means for association it is different. Exactly. For association it will be slightly different. What about for association? How comes for association? For association, the degree of association is equal to 1 minus I by 1 minus 1 by n. Alpha degree of association is equal to 1 minus I by 1 minus 1 by n. What is n here? n equal to 2 for dimerization, n equal to 3 for trimerization, so on. If it is dimerization, 2 units combining, n equal to 2, trimerization, n equal to 3, tetramerization, n equal to 4, like that. So there can be numericals based on this content also. So definitely you are going to encounter numericals based on abnormal colligative properties. All those numericals we are going to do in the classes. Consent. Okay. This is what the content in the chapter solutions. Let me remind you from the beginning, from where we started. It is solutions, homogeneous mixtures, 9 types of solution, saturated, unsaturated, supersaturated, 9 combinations, concentration terms, mass percentage, volume percentage, molarity, normal, etc., normality, etc. Then solubility, Henry's law, solubility of gases in liquids, applications of Henry's law constant, Raoult's law, vapor pressure, Raoult's law, ideal solution, non-ideal solution, positive, negative deviation, right? Then in this non-ideal solution, positive, negative deviation, there are azeotropic combinations. Non-ideal solution, positive deviation shows lower boiling azeotropes. Azeotropes means constant boiling mixtures. They form lower boiling azeotrope, while non-ideal negative deviation, they show higher boiling azeotrope, maximum boiling azeotrope. What are azeotropes? You might have heard about. Constant boiling mixtures are called azeotropes. 1 or 2 examples quoted in the NCERT. Then colligative properties. Relative lowering of vapor pressure, elevation in boiling point, depression in freezing point, osmotic pressure. And all terminology connected. Finally, abnormal colligative properties and Van 't Hoff factor and the related Hall formula. Degree of dissociation versus Van 't Hoff factor, degree of association versus Van 't Hoff factor. Degree of dissociation, alpha is equal to I minus 1 by n minus 1, and degree of association, alpha equal to 1 minus I by 1 minus 1 by n. Once again, here when alpha is 100%, I is equal to 1 by n. Here when alpha is 100%, I is equal to n. Here when alpha is 100%, I equal to 1 by n. This is association, this is dissociation. If there is neither association, dissociation, I will be equal to 1. Ideal solution. That's all from the chapter. With a new content, new chapter, new theory, we will meet in another class. Till then, bye, see you, take care, study well. Okay, bye.